When you're out in space, you realize how important the Earth's atmosphere really is. Astronauts have to carry an artificial atmosphere along with them, enough to last until they return to Earth.
Apollo, this is Mission Control. We show 5 minutes till re-entry. Roger, command module attitude nominal. We're starting to read atmosphere. 2 Gs.
In the outer reaches of the atmosphere, air as we know it is almost non-existent. There are only scattered particles of gas. At an altitude of approximately 120 kilometers, gas particles are more numerous. The atmosphere is more dense. In this layer of the atmosphere, a spacecraft is heated by friction as it speeds toward Earth.
Roger, we really got a fireball up here.
In the stratosphere, where commercial jet aircraft fly, the atmosphere is dense enough to allow parachutes to decrease a space capsule's speed. The stratosphere extends from about 10 to 50 kilometers, or about 7 to 30 miles out in space. The troposphere is the layer of the atmosphere that lies closest to Earth. This is the region where we experience clouds, wind, and weather. This is the air we work and play in. This is the atmosphere that supports all life on Earth.
Splash down. Roger, confirm splash. Spacecraft is in stable 1.
The atmosphere. It can burn a spacecraft to a cinder, or ripple its fingers through your hair on a sunny afternoon. Normally, we can't see it, but we know it's always there, and always changing. Although we can't see the gases that make up the atmosphere, we can observe and measure their effects. We know, for example, that the greatest part of the atmosphere, almost 80% by volume, is nitrogen, a gas that reacts only slightly with other chemicals. We also know that the atmosphere contains oxygen, because without it, nothing would burn, and most living things would perish. Carbon dioxide, which is necessary for plant life, is present in small amounts, along with other gases like xenon, argon, helium, and methane. Water exists in the atmosphere as a gas, which we call water vapor. When water vapor condenses to its liquid or solid form, it may become visible as clouds, or fog, or as droplets on the side of a cold pitcher. This thin layer of gases, held to the Earth by the force of gravity, is our atmosphere, or what we call simply air.
Although we don't often think about it, the atmosphere has weight, and this weight exerts a pressure that affects everything on Earth. Atmospheric pressure works in all directions. Here, the atmosphere is pushing upward with enough force to hold water in this cylinder. When we allow it to push downward as well, opening the top of the cylinder equalizes the effects of air pressure. The water can be pulled down by the force of gravity. The pressure of the atmosphere can be measured with a simple mercury barometer. Air pressing down on the mercury in this container supports the mercury column in the sealed tube. On this beach at sea level, air pressure is sufficient to support a column of 76 centimeters. When the barometer is taken to a mountaintop, the column falls to 61 centimeters. This indicates that there is less air pressing down on the mercury. The atmospheric pressure is lower. The higher the altitude, the lower the pressure. What causes motion in the atmosphere? In a word, the answer is heat. Using special lighting and photographic equipment, we can demonstrate the effect of heat on air. The candle's flame is heating the air around it. Heat causes molecules of air to move faster so that there is more space between them. At the same pressure, a volume of warm air contains fewer molecules than the same volume of cool air. The warm air is lighter, and because it is lighter, it rises. On a hot day, you can see the same process at work as warm air rises from the Earth's surface. The energy to heat this air comes from the sun. All the motions of the atmosphere, from the slightest breeze to the most violent storm, are powered by the sun. Less than 1/billionth of the sun's total energy output warms the Earth and provides energy for all its life. But not all parts of the Earth receive the same amount of the sun's energy. We can demonstrate this using a globe, a light source, and a screen that allows equal amounts of light to pass through each opening. The amount of light falling on the globe can be measured. Near the North Pole, we count 6 units of light falling on an area of approximately 25 square centimeters. At the equator, 12 units of light fall on the same area. The light energy falling at the pole is less concentrated than that falling near the equator. Over tropical seas, the sun beats down throughout the year, heating air and evaporating water day after day. Near the Earth's poles, temperatures may be more than 100 degrees colder. From what we know about hot air, we can assume that the air at the equator is rising. What is happening to the cold air at the poles? Adding a cold source to our special photographic setup suggests the answer. While hot air near the candle is rising, cold air near the dry ice is sinking. Other fluids behave in much the same way. Here we apply a heat source to one side of a closed fluid container. Dry ice encased in plastic is used as the cold source on the other side. As we would expect, the heated fluid is rising and the cooled fluid sinking. But there is also horizontal motion. A cycle has developed. The cycle is known as a convection current. In a similar manner, the atmosphere moves in huge convection currents to balance the temperature differences between the poles and the equator. Warm air from the equator rises and moves toward the pole. There it cools, sinks, and moves back toward the equator to continue the cycle. These convective movements of the atmosphere are what we experience as winds. But we know that winds don't always blow from north to south. In fact, they rarely do. Obviously, there are other factors that govern the movements of the atmosphere. One of these is the rotation of the Earth. The atmosphere rotates along with the Earth, making one complete turn in about 24 hours. But not all parts of the atmosphere are traveling at the same velocity in space. In approximately 5 hours, the Earth and the atmosphere rotate this much. Air near the equator moves a greater distance in space than air near the pole, as shown by these red lines. Because it moves farther in the same amount of time, air near the equator has a greater eastward speed or velocity than air near the pole. This difference in velocities has an effect on winds that travel across the Earth's surface. In this demonstration, the northern hemisphere is represented by a flat turntable. The outer edge of the turntable corresponds to the equator. The center represents the pole. A projectile shot from the edge of the turntable toward the center, or from equator to pole, travels in a straight line. The ball is inked so that it will trace a path across the disk. Now the turntable is set in motion to simulate the Earth's rotation. The projectile is fired several times. Each time, its path curves to the right. The path of a projectile fired from pole to equator also curves to the right. In fact, no matter where the projectile is fired, its path curves to the right. The same force affects the direction of winds on Earth. If the Earth were not rotating, air would travel in straight lines between the equator and the poles. But the rotation of the Earth deflects these winds. In the northern hemisphere, air is deflected to the right or eastward as it travels from equator to pole. Air moving from pole to equator is also deflected to the right or westward. In the southern hemisphere, moving air is deflected to the left or eastward from equator to pole and westward from pole to equator. This deflection, the result of the Earth's rotation, is called the Coriolis effect. Convection between the poles and equator, the Coriolis effect, and other influences like the distribution of oceans and continents explain the global wind patterns that we call trade winds, prevailing westerlies, and polar easterlies. But there is much more to atmospheric circulation than these global patterns. What the wind and weather are like where you are depends on a number of additional factors. For example, mountain ranges form barriers to air movement. Bodies of water can also play a part. Land absorbs and loses heat faster than water. So, a shoreline can be the site of local winds caused by small-scale temperature differences. At any given time and place, many different factors come together to determine the movement of the atmosphere. And the movements of the atmosphere are what give us our weather. Gentle spring breezes or violent storms. Storms occur when concentrations of energy exist in the atmosphere. They are an important part of atmospheric circulation.
From the beginning, man has been able to see the atmosphere only from his limited vantage point, the surface of the Earth. Now, space exploration and modern scientific techniques have given us another look at the atmosphere. Photographs transmitted from weather satellites give a picture of the atmosphere's constant change. In field studies all over the globe, meteorologists analyze the physical forces that influence global and local circulation patterns. The atmosphere, the air we breathe, the weather that affects our day-to-day activities, it is such an important part of life on Earth that we usually take it for granted. But we are beginning to realize that the atmosphere that makes possible life as we know it is only a very thin, very delicate envelope of gas surrounding the Earth. We are also beginning to realize that our activities are having an effect on this thin, vital envelope. Each year, we pour millions of tons of pollutants into the air. How do these substances change our atmosphere? How does the motion of the atmosphere affect the quality of life?